Okay, I think we'll get started. So today is our first lecture where we're starting to head towards the area of chemical kinetics. And this is the area of chemistry that is going to address the question, how fast will a chemical reaction happen? Well, we have to take a couple of steps in order to actually get to some chemistry. And the first of these is what we'll talk about today, which is physical kinetics. And we're only going to pull one special thing out of this idea, and that's the so-called Maxwell-Boltzmann distribution of speeds, which tell us how the speeds of molecules are distributed across a gas. And from that, then we'll be able to get a few averages and be able to talk about sort of the average or typical behavior of the gas. This will serve as a basis then for our next lecture, which will start letting these gas molecules collide. And of course, if we're going to do some chemistry, we've got to get molecules to collide. And so that will lay the physical groundwork for then moving into the area of actually having chemical reactions happen and watching how fast reactants disappear and products form. Okay, well, let's attack physical kinetics today now. So let's say we've got this container, it's got a gas in it, and we ask ourselves, what is the distribution of particles within that gas container? Well, we could then stick a coordinate system, let's say right along this back edge of this container, and the positions of these gas particles would be could be plotted pretty much exactly as they appear physically in this box. And so we would get a distribution of particles that are in the area inside the box, and then nothing outside of the box. We would also expect physically, if the gas is at equilibrium, this has just been sitting there forever and will sit there forever in the future, then it's at this equilibrium. There's a certain amount of gas particles per volume. That's called the number density. The number density. We say, well, what is our chance of finding a particle if we look at a position X? Well, let's look at that in this coordinate space, so just the XYZ coordinates of this, and we're going to, or physically, we would say that this distribution is stationary. Now, it doesn't mean that the individual particles are moving. They're moving like crazy. But on a whole, the box is not moving one way or another. The distribution isn't going all the way to the top of the box or anything like that. It's staying essentially the same from a global perspective all the time. And so that type of a distribution is called a stationary distribution, or it's a stationary process. So you have stationarity here. So that will take this function f, we'll just say little f here is going to be what's our chance of finding, or how many particles in a particular region. And we would say, well, f is not a function of time, then it'd just be a function of position. And I should actually probably make this, make that an r. So of the XYZ position. And this would be a very simple statistical distribution. It would be a constant or uniform distribution that's related to the number density. So we would just be proportional to the number density. And so we would be n, number density, times a little differential box inside at a given position. If we're inside the box, so this would be in the box. And then 0 if we're out of the box. And so that certainly would describe this distribution of gas particles, but it doesn't allow us to do much else with it. So it isn't a very handy way of categorizing or describing the distribution of particles in this gas. So what we're going to do instead is we're going to move to velocity space. And so how are we going to do that? Well, let's take a given molecule, let's call that molecule I. Right, let's say this is molecule I right here. And molecule I will have a particular speed and direction, or a velocity vector associated with it. And so we can express that over here in velocity space by just casting that vector as its xy, vx, vy, and vz, or the velocity in the speed in the x, y, and z directions. And so this is maybe a little bit this way, so we're in a positive y, negative z, and maybe a positive x. So this would be the position of that ith particle. And then we might have the jth particle over here going this way. Now it has a positive z and positive y, maybe a negative x, so maybe it's over here. That's the j. So these vectors that are associated with each one of these particles then represent a distribution of points in velocity space. And let's physically try to think about that distribution. Well, for one, it's going to be stationary. So yes, each individual is changing its velocity vector, but on a whole, the distribution is stationary. So we expect this function to be stationary. Oh, and let me say one more thing. We can, it's going to turn out, and we certainly are free to do this, we can talk in x, y, z Cartesian coordinates, or we can talk in spherical polar coordinates. And if you haven't seen spherical polar coordinates, that's just another way of addressing a point in space. I'm not going to say too much about it now, but in order to talk about this point in space, we need an x, y, and z, or in this case, a vx, vy, vz. Okay, that's one way to describe it. Or we can describe it as the distance from the origin. That would be v. That's going to be the magnitude of the velocity. So physically, that's going to represent speed. And then the angle it makes with the vertical. And then what we do is for this coordinate system, the angle, if we were to cast a shadow onto the xy plane, the angle we make coming out of the or coming out from the x-axis, from the x-axis to the y-axis. So any given point here can be described in angle and length coordinates. Now, what does the length mean here? This is the speed. Speed, and then these tell us the direction. And so vectors, speed and direction. Now, we're stationary, so we drop time, and we should be just a function of speed and direction. But let's think about this. If there was a net direction, then the particles would move in that direction. So let's say there was a net direction this way. Then they would all be stuck up against this side of the box. So there must be no net direction. The average direction has to be 0. And let's think about the shape of an object that would have that average direction be 0. It would have to be angle independent. So if we look out, it would be spherically shaped. So this should be a spherically shaped cloud of points centered about the origin. And as we go out, we would expect to find less and less particles as we get way out here, because if we're way away from the origin, our speed is very high, meaning that particle has an inordinately high energy. So we would expect that to drop away. Now, we don't know exactly what it'd be like in the middle, but we expect it to drop away as we get to very large speeds. And so if we were to look at this, it would look like a spherical cloud of points. And so that's isotropic, independent of angle. And so we become just a function of the speed. And that's called Maxwell's distribution. Sorry, that's just a distribution of speeds. We're going to derive something called Maxwell's distribution of speeds, or not to derive it, but we'll talk about the actual distribution. But as of this point, we can see just through stationarity and the fact that the particles don't just all go to one side of the box or the other, so isotropicness, that we should have a distribution of speeds, not velocities. Okay? All right, so this becomes a one-dimensional function, or one independent variable. Okay, so now where do we go from here? Well, we're going to just talk about two things that are coming from courses down the line. So the first is from statistical mechanics. And we are not doing any significant statistical mechanics in these introductory courses. We just have to build to that. Now, we do want one idea coming from that, and that's this Boltzmann distribution. This is going to be very important to us as our curriculum develops and as we're further up in higher level courses. But for now, we're just going to say that the probability or the chance of finding a particle at a given energy. Okay, so this is if we pick out one of these particles at random, what is the chance of having a particular energy? And it's given by just some normalization constant. So all this is doing is to make sure that it's a probability, a chance to pull that out. And then the energy is penalized exponentially. So we get an exponential penalty on a very high, on energy. So the higher energy is getting killed off like an exponential function. And then this is mediated by temperature. So if we have if the system is at greater temperature, there's just more intrinsic energy from being at that temperature, so that we are really looking at the ratio of the energy to this so-called thermal energy, or KT, K times T. K is KB. KB is the Boltzmann constant, so that's joules energy per Kelvin. So K times T is an energy. So you can think of that as the thermal energy around. So if we're at a low temperature, we don't have much thermal energy around. It's hard for a particle to have really high energy. And so it's this ratio that matters. Okay. So let's say the energy, what's the chance of the particle having 10 times the amount of thermal energy? Well, that would be e to the minus 10. So a pretty small chance of that. Then something from Calc 3 that deals specifically only with geometry, and that is when we go to spherical polar coordinates, this little element here, so-called volume element. So if we're at a point, what is a little bit in each of the directions? Well, now each of the directions is r, theta, and phi, not x, y, z. So, or I guess v, theta, and phi. The so-called volume element, then for an isotropic system, so we're doing a couple things at once here, is this little extra factor of v squared. And so this is coming just from the geometry of the coordinate system. So we have this physical thing, this Boltzmann distribution, and then we have this geometric thing that comes together to answer the question, what is the chance of finding the particle at a particular speed? What is the distribution of speeds? Well, so here we see it. This is the so-called Maxwell-Boltzmann distribution of speeds. And what can we see up here? Well, let's look at this first. Okay. That's 1/2 mv squared. That's kinetic energy. This is T. Okay. And for these gas particles, what we're assuming is that all the collisions are elastic, and there's no internuclear forces. So there's no intermolecular forces. They're just hard spheres colliding. All collisions then conserve energy, and the only energy is kinetic energy. So E equals T for this, and we have conservation of energy and momentum. So that's our E equals T. Okay. And so that's up here. And what does E depend on, or what does T depend on? It depends on the speed. And so there is how it depends on speed, 1/2 mv squared. Then it's over kT. I guess I should have a kb here. So it's over kT. Then what do we see here? Here's that geometric factor. Here's that geometric factor. And then this is all just a normalization factor, so that when we so that it really represents a probability distribution. This, notice it's a constant, but it does depend on temperature. Again, I'm missing my B here, kBt, and the mass of the particle. So the parameters of the model show up in that normalization constant. Okay. All right, well, let's plot this and see what this looks like. So if we're going to plot this, it's actually here. It's actually so we're going to plot f as a function of speed here. And let's do it in pieces here. So we're just looking at the shape. That's all we're really interested in. So I'm going to plot this v squared, this parabola. Then I'm going to plot this. Well, this is like e to the minus x, or a Gaussian or a bell curve. So that's going to look something like this. And the total then is the product of these. So if we don't worry about, we're just worrying about the shape, not worrying about the magnitude here, so we won't put any scale on this. Then we multiply these two things. Here, this times this is going to be very low, so we're going to follow the parabola at first. Then we have a situation where this is going off to infinity and this is going to 0. But if you remember from algebra, exponents always win, and this is even stronger than an exponent. This is a Gaussian behavior or bell curve, so that wins for sure. And so we get something that looks like that. And so that's our distribution of speeds. Now let's look at the role of temperature. So let me plot that again. Let's plot for T1. And now let's raise the temperature. So let's plot for T2 greater than T1. What's going to happen? Well, let's think about this. Let's look at the math first from one perspective, then we'll think about it physically. So nothing's going to impact this. There's no T here. This multiplier out front, T's in the denominator, so the overall size is going to come down. And now the real action is up here. This is going to impact the shape. So if T goes up, then the denominator of that exponent goes up, meaning the numerator has to be bigger in order to have the same effect. So this extends out further. And so what we'll get here is an extension and a widening of that curve. All right, so let's think about that physically. Let's think about the two things. We have a shift and then we have a widening. So if we're at a cold temperature, kT is our thermal energy, right? So if we take K times T, that's our energy that we have available to the system for being at this temperature. If it's cold, if temperature is low, we're not going to have a lot of particles that are way high in energy. So that distribution is going to be moved towards lower values or shifted this way. Then when we heat it up, it will shift the distribution the other way. Now, the widening, what we can think about here is there's an analogy that I like to use is if we're in a class and we go all out to the track by the gym, and if we were all just walking along the track, right? We walk at, let's say that's lower temperature, lower energy. We walk at different paces, so we will start to spread out along the track. But if we were to all run, let's consider that higher energy, we'll all be moving faster. Right? So our average speed would be faster for the whole group. But the spread, the difference between our running speeds across a whole class versus walking speeds across the whole class will also spread out. It's the same thing's happening here. As we give the system more energy, the range of the possible energies spreads out. Okay. So now the last thing we need to do is to calculate some averages. And that's a calculus thing. If you've had some Calc 2, you've probably looked at doing some averages. So it's just integrating this function times whatever it is we want to average. I'll let you look at that if you've done some calculus. Here I'll just state the results, the important results that come out of this. Well, we can talk about average speed. And if we calculate the average speed, so what is the average speed of this distribution? We expect it should depend on temperature, and it should be proportional to temperature. And indeed we see that. In fact, it is proportional to the square root of temperature. Then there's this 8k pi. Those are just sort of numbers that come along. We'd expect a k to be there because k is sitting in here. And we'd also expect the mass. Now, how's the mass going to change things? Well, if we have a heavier mass, to go the same speed requires more energy. So we would expect that the velocity should be inversely proportional to the mass of a given particle. And so it is according to the square root. Now, we've talked about this before. K, I keep forgetting the B's. KB times Avogadro's number is R, and mass times Avogadro's number is molecular or molar mass. And so we can multiply top and bottom here by Avogadro's number and get this into a per mole form. And there we see 8RT over capital M, the molar mass. And so that's another way you might see this. So this is a per molecule in this language, and that is per mole language. What you'll see in your Gen Chem book, when you look at this section, it will be in the chapter on gases, towards the end of that chapter, in whatever chemistry book that you have. And one typically narrows in on what's called the root mean square. So this is the average of the square of the speed, and then take the square root of that. So it turns out it's a little simpler form, kind of, 6 of one, half a dozen of another, what you use here, but it's 3RT over molar mass. So again, we would expect it to have the same dependence on temperature and mass. And then here's something that's really interesting. This is a key idea, and we'll come back to this a couple of times, well, at least one more time in the course here, in this particular Physical Chemistry, Introduction to Physical Chemistry 2 course. The total kinetic energy, the average kinetic energy, so I should put a bar over. The bar over means average. So the average kinetic energy is 3/2 kT, or 3/2 RT. And this is a statement of something we'll talk a little more carefully about in the future, and that is the so-called equipartition of energy theorem. And what this states is that energy distributes itself equally in any possible so-called degree of freedom. And we're thinking about these as just point masses, so they can go this way, or this way. So X, Y, Z, they have 3 independent translational degrees of freedom, and that's it. There's no internal structure, so no vibrational freedom, no rotational freedom. So we only have the 3 degrees of freedom, or DOF here, degrees of freedom. The equipartition of energy theorem says that we get 1/2 RT per degree of freedom. And so for a 3-dimensional gas, we should get 3/2 RT for our energy. And that's precisely what is calculated here with the Maxwell-Boltzmann distribution of speeds. The equipartition of energy is coming from a sort of a different theoretical perspective, but thankfully, and in some sense, of course, the result calculated from the Maxwell-Boltzmann distribution of speeds is in agreement with the equipartition of energy theorem. So this will also be in your book. This is a very important theorem that makes its way into the general chemistry book as well. So I don't have a lot more to ask of you for this, because it does, to really get into it, it does involve some calculus. I should say it is fun to see all these come out if you know your calculus and can just plug into Mathematica or Wolfram Alpha, or if you use some other program for doing your symbolic math. These pop right out, which is pretty interesting to see. So if you've got that experience, then I encourage you to just play around with that. If you haven't, then just go to your book and it'll focus in on these two, and you can learn a little bit more about that. It will talk about effusion, which we're not going to talk about here. We'll talk a little bit about diffusion later. So that will be in that little section of your book as well. So you can read up on that, but I won't be talking about that here. The next lecture, we are going to talk about collisions. So we're going to use something related to the average value of speed to see molecules collide, and we'll be able to calculate a collision frequency and then the so-called mean free path. How far does a molecule go before it collides? And that will be the basis for collisions that will then initiate a chemical reaction.